I'm going to be working up to 6 new objects today if all goes well, but the one of them that I just thought of last I'm just going to show you and then not use because I just want you to know this exists. It will come in its own good time, but you will need it probably before I need it because I know in advance what I'm going to do and you don't, so your work is going to be more complicated than my work. Right? So if in an object box you type PD, then you get a thing, and when you click on it you see a sub-window. And the sub-window is yours to put anything that you want in, and it will stay there. And it'll be a part of the patch. If you close it, it doesn't actually go away. It's still there and still doing whatever it was doing before. So it's part of the running patch. But it is a part of the running patch that you don't see. The reason I'm going to be reaching for it probably first off is going to be when I have too many tables running around and they start crowding out the functional part of the thing. So a very normal thing to do is take all the tables that you're using, the arrays, and stick them in a sub-window so that you don't have to look at them all the time, but so that you can look at them whenever you want to check them out. And it's a single click, so I'm trying to be good to people's wrists. Okay, so that's all, yeah.
Well, is that something where naming conventions will get messed up if you have multiple batches going?
Only in one very crazy sense, which is that you can actually send a message to the window to do something like open itself. And in that case it will actually pay attention to its own name. Otherwise this name actually only functions as a thing that it prints up on the window so that you can tell what's what. And especially so that your window manager can tell you which window is which on the bottom of your screen, which is useful. So it's a good thing to name them, although you don't absolutely have to. And name them something that actually has something to do with what you want to put in there so that you can find it later. The other objects, let's see, you might have already seen this and might not have. There's a thing that looks like a button but isn't. This is actually a kind of number box. I'll use it to turn metronomes on and off pretty soon. But the basic trick is, it's a, let's see, I'm going to make a new window and start showing these things off. Okay. So this thing, which you get on the put menu under toggle, is a kind of number box which makes numbers that are which are 1 and 0. So 1 and 0 is computer language for true and false. Most people who study computer science learn that true and false are constants which have a different type from 1 and 0, but PD doesn't do type. So 1 and 0 are either usable as numbers or as logical values. In fact, it's even better than that. Any number that is not 0 in PD, like 4 times 10 to the minus 7th, 0.4 times 10 to the minus 7th, that ridiculous number is actually true because it's non-zero. By the way, yeah?
So when you use E in this one, it's a lowercase and stuff like that?
Oh, you can, I think you can use either, let's see. I didn't think about that. Yeah, oh yeah, that's interesting. It'll read either, but I think it will represent it using lowercase. And most computer languages will use either lower or upper E interchangeably.
I just wanted to make sure there's like a little E I know, it's like Euler's number and big E like
Depends on the language. Like big E also could be energy, so on. Okay, so yeah, this is 4 times 10 to the minus 8. If you ever want to express a number like that, use exponential notation. Is that what it's called? Well, okay, use it. All right. Oh, and by the way, even though the value true, when you say it is 1, hello. That is horrible. I didn't write this object. It should say 1 when you re-click it, which it doesn't. So now I have to fix it. Okay, very good. I didn't know that. All right. So anyway, it transmits whatever value you put into it through, which is correct behavior. And then when you tell it to be on, it should probably say 1 instead of some crazy value like that. Yeah?
Is the negative number 0 or is that?
Negative number is also true. Hello? Oh, right. I can't type into that one. I have to get into edit mode. Yeah. So 0 is the only falsehood. It is a misconception that people get when they start programming using floating point numbers that they can't hold values accurately. Like the integer 5, if you express it as a floating point number, is somehow not exactly equal to 5. 5 is equal exactly to 5, even if it is expressed as a floating point number. However, 0.1 is not equal to 0.1 when you express it as a floating point number, because it becomes a repeating decimal in binary, and then it will get truncated. But you can represent integers, including 0, exactly using floating point numbers and not expect truncation error. Integers do not get truncated below values of plus or minus 8 million. After that, they do, because there's only 24 bits of mantissa in the number. And go study computer science if you want to know more about that. Okay, so there's the toggle switch, which is, by the way, excellent for turning metronomes on and off, which I think I've shown you, but I can't remember if I used the toggle. I don't think I did. So here's a nice metronome. And this leads to my next topic. Oh, yeah, so let's put a nice bang so we can see the metronome going. All right, and then so this is a combination of objects that you see all the time, and of course you could use a number box, but then you would be obliged to scroll the number box up and down to restart the metronome, which is ugly. Whereas this is appropriate and convenient. All right, I showed you that so that I can show you this. I'm about to call attention to the central source of confusion in all of computer music, which I've, by the way, visited a couple of times in the past and will have to visit again a few times too, which is the distinction between doing things with messages and doing things with signals. So, for instance, one way that I've taught you to count to 4, or to count to some number, is using signals. I'll do it over here. Make a phasor. Let's count to 5 for reasons I'll explain later. I'll run it at 1 hertz, and then I will multiply it by 5. And then this will generate a sawtooth wave which ranges from 0 to just below 5 in value. And then I could use that, for instance, to read values in a table, which I've shown you how to do. So, for instance, let's make a nice array. And it will be called, oh boy, okay, table 125A. Oh, and I was typing in the wrong place. Okay, call it that. Oh, those are big points. Oh, right, and then it forgets that it was points, so I have to say it again. You are, whoa, that was interesting. Oh yeah, you are points, and you have only, let's say, 5 of them now. Did that work? That did not work terribly well. It worked well enough. Okay, little fence post bug. It really didn't leave room for the last one, did it? Let's fix that. Ta-da. Okay, table. All right, and now we can do something like get those values out and use them as the frequency of a tone that we'll listen to. So, for instance, let's do a tab read T January 25th, first try. Oh, right, tilde, because we are signals. This is the thing that I'm trying to warn you not to be confused about. And now we've got something that we could drive a sequencer with. All right. In fact, I won't go further than just to do that. And one thing about tab read tilde is that it's truncating these things to integers, which you could do in a variety of other ways. But the table is the thing which truncates to integers that you've seen, which is why I hauled a table out just there. All right. Next possibility. Maybe it would be interesting to do this using messages. That would mean rather than each time the oscillator tells you it's time for a new thing, which means it's going to happen regularly, it waits for you to tell it to do the next thing, please, according to some other source of time or some other source of, well, events. So, such as this source right here, which is a metronome. But it also could just be me doing this by hand, right? Okay. Well, you can do that. And the way you do it is this. this is what's the right word? This is one of those paradigmatic ways of programming in PD that is particular to PD or Max, and this won't help you do anything except survive using PD and Max, as far as I know. This is not actual knowledge. This is just craft. Okay. So what you do is so we're going to make a counter, and it's going to count up 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, like that, which is therefore repeating with a period of 5. Okay. How do you do it? Well, the first thing you need is a number, and numbers are held in. Oh, let's call it. Oh, I haven't even told you about this object yet. Have I? You can have storage. Okay, you've seen a lot of storage in PD because whenever you say +5 or plus, which has an inlet, that inlet is a storage item. And so a lot of objects such as plus or the oscillator are perfectly happy to store numbers for you, which are the parameters or the arguments of their operation. Okay. However, sometimes you need to talk about storage explicitly, which is indeed what is going to happen right now. And so we need to have a thing which just exists for storing numbers. This also could be no, I was thinking it could be a number box, but I think it just has to be what it is for what we're going to do next. And in fact, now I have to apologize because our object count just went up to 7. Maybe we could, oh yes, we do need mod too. So your new objects are going to be numerous today, so I'll hold off on inflicting new objects on you next time. So now what we're going to do is so the float, what does float do? Float does this. You put a number in, put a number in, and it says thank you. Oh wait, go away. Oh well, I'll put that here. And it says thank you very much, I know my number. This is acting exactly like a regular inlet acts, right? And then when you say bang on this side, it says what was the number, please output it. All right, clearly a very useful object. It's almost you could almost do this with a plus, because you can actually send a bang to plus, and as long as the first inlet thinks it's 0, then it will just output the second inlet because it'll add them. But that would be confusing to look at because it looks like it's an adder and it wouldn't be. So it's better to actually use the object which is explicitly just doing what we're using it for, which is storing a floating point number, therefore called float. Yeah.
What happens if you look up the metro to that bang?
What'll happen then is let me do another thing, which is put a flasher here so that you can see when it's actually outputting, because 53 is just 53, but if I send more 53s, you won't see anything unless I put this bang here. So now what's happening is the bang is going to flash whenever it gets something. This is going to be the number that it actually got, which might not change, right? So what happens if we hit this with the metronome? It just says 53, 53, 53, 53 5 times a second. Okay? Could be useful. But let's see, here's something that could also be useful. Let's take it, and every time a number comes out, we'll just add 1 to it. And now we have something cool. We've got the genesis of a programming language. Right? If you can count, then you can do stuff like, well, you get the idea. All right, this is a loop, and notice a few things about this loop. First off, this is uglier than just writing a loop in C would be, because when you write a loop in something like C or any programming language that's based on text, you actually see the steps of the loop in the order that they are supposed to happen in, because programming languages tend to go down, statement 1, statement 2, and so on like that. PD doesn't work that way. PD goes along the lines, and so you have to do a lot of extra nonsense, which is to actually sew the loop together into a loop. Right? So this is actually not as efficient a way of describing a loop as you would have in C or something like that, where you just type 8 or 9 characters and you've got a loop. Okay. Another thing is, just to tell you this, usually when you do this, you don't bother with this, you just do this. Oh, by the way, I disconnected it, and so now it's just 399, but now it's counting again. It's just counting in a way that uses the property of float, but doesn't include the float it doesn't include the little thing that I put in to demonstrate the float. This is better because, as you might have already noticed, the more stuff you have flashing or drawing numbers on the screen, the more your CPU time is being eaten up by just updating the screen, which of course is a useful thing for knowing what's going on, but is also competing with your CPU time, competing for your CPU time with the thing that you're actually trying to do, which is make beautiful music. So you don't have to have unnecessary number boxes, and in fact it's better not to a point. And by the way, if you do want to have a lot of unnecessary number boxes, throw them in a sub window and keep it closed, and then PD doesn't have to draw them, and then you won't be eating the CPU time after all. That's an important clue to, oh, my patch, which covers 5 screens and you have to scroll in order to see it, is starting to run slow, right? Well, okay, put a bunch of it in a sub patch and keep it shut, and then it won't be drawing the stuff, and then it won't run slow anymore, at least for that reason. All right. So now, so the first observation about this is that this is a bad way of making loops if you're used to using programming languages, but it's what you get in PD. There's no programming language here. Second thing is, notice that it actually looks like a tree, even though it looks like a loop to the untutored eye. This connection is going into the inlet of float, which doesn't cause float to do anything. So that when a bang comes into the float, the sequence of things that happens is, in some order or another, these three, the number goes out these 3 lines, one of which is this line, which gets added 1 to it, and that gets put into the float. That does not affect what the other 2 people got, because this message was output, and it's there, and the float, when it remembers this new value, will use that to change anything that it might do in the future, but that doesn't affect the rest of what happens as a result of passing that message out of its output. Right? That would be reentrancy or recursion. You can do recursion, but don't. Okay, so the reason this works and doesn't give you an infinite loop is because, in fact, this chain of operation actually stops there. And if I want this not to work, save this just in case this does. Oh, wait. Oh, I don't have a name. 2 loops. Okay, we've saved it, so now I don't feel bad about doing something that might bring PD to its knees, depending on the OS. Come here. Let me take that other line out and just hook it up here. And then we get error messages about stack overflows. Okay. That doesn't work. Oh, and it does horrible things there. Yeah. That doesn't work because then the float says add 1, the add 1 says okay, do it again, and so on. And every time the metronome bangs, it tries to add 1 to it an infinite number of times. And it actually only got up to some number of thousands before it just said, give me a break, and stopped. Rather than allowing my PD or even the operating system to crash, as might otherwise have happened. Oh yeah, and now that we're here, loops are great, but the first thing you learned in computer science about making loops is there are 3 steps to the loop. There's the thing I haven't done, and then there is, there's one of the 3 of which I've done, which is updating the thing each time around the loop. I haven't told you how to start it, and I haven't told you how to stop it. In PD, things aren't started and stopped so much as they're always sitting there latently ready to do one thing, whatever it is that they do. They're waiting for events to turn them on. So starting and stopping the loop doesn't make sense in PD the way it does in a computer language. But initializing variables, which is typical of what you do at the beginning of a loop in a real language, is a useful thing to be able to do, and you do it like this. You say, give me a value of 0, please. And you put it right in where these numbers go in. And of course, when I whack a 0, it's going to happen between 2 of these bangs, because no 2 things happen simultaneously, even though they can happen with a difference in time of 0. So time works in, what's the right word? I don't know the word. Time works chunkily in PD. So this will set it to 0, and then the next time it gets banged out will come 0 here. Oh, right. So it starts at 0, this loop. Or it starts at whatever you put in. It doesn't increment first, it increments after. All right, there's a loop. Suppose you want it to count 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and so on like that, instead of doing this thing. There are two ways to do that. There's the way everyone thinks of first, which is to test whether the number equals 5, and if so, to bash it to 0. That is not going to be so great because you're going to see the value 5 and then the value 0 unless you're very careful. So let's do it the smart way, which is simply to ask for the remainder when after dividing by 5. Oh, by the way, I've disconnected this so it can't update anymore. It's stuck. And now I'm going to say, how about mod 5? So here's the mod object coming at us. And now we have our wonderful counter that goes from 0 to 4 like that. And now, in fact, if we want to, we can do the same operation as here, except now we can actually use a tab read without a tilde and look at it. And now we're looking at the 5 values of the table. And I didn't set the range of the table to be, sequencer type range, so it's just what you're seeing. Yeah?
So that's all it is, it's just as arrangement?
Well, mod itself is an arithmetic operation. What it is the remainder of that you get when you divide the left inlet by the right inlet. And it works in this case because 0, 1, 2, 3, and 4 give themselves, but 5 gives 0.
Is it like modulus in Java?
Might be. I don't know Java, but could very well be the same thing. There's only one correct way to do it. It's almost like the percent sign operation in C, except the percent sign operation in C is wrong, because if you say -5% 3, you should get +1, and instead it gives you -2. So mod actually does the mod thing, which I hope Java's modulus does, but I suspect it doesn't. Which is, if you feed it -1, -1 divided by 5 gives you a remainder of 4. Oh, say -1. Why? Because what's the biggest multiple of 5 that doesn't exceed, that's smaller than -1? Well, it's -5. And then you have to count up 4 from there to get to the actual number -1, so the remainder is 4. All right, that's mod. There is a mod tilde. Oh, yes, so this as well, along with tab read and along with plus, come in control versions, and they come in signal versions. And there are times when you want to use the one type of thing, and there are times that you want to do the other. Advantage to doing things in control land. Advantages, I can think of 3 right off the bat. Potential advantages for doing things the control way. One is that it is much easier to do things irregularly. For instance, if you want to count incoming network packets using net receive, which I won't tell you about. Well, they come in and you might regard them as an event, such as a bang. Or me, I'm clicking on the thing. I want to count mouse clicks, same deal. You don't know when they're going to happen. You don't know whether they're going to happen at all, and you don't know how many you're going to get. And that's the sort of thing that you can do effectively in using messages, and less effectively using signals. Okay, that's advantage number 1. Advantage number 2 is that you can actually hook the things up to a number box and see them. Whereas signals, you have to work harder to see what they are because they're going by at 44,000 units a second or something like that. And so it's not feasible just to put it in a number box and look at it. You have to either say print tilde or throw it into a table or an array and look at the waveform or something like that. So it's much more convenient to debug stuff here. And third thing is it's much easier to do things conditionally. Or rather, it's possible to do things conditionally, I guess I should say. Signals are always happening, but messages, you can, I haven't shown you the primitives for doing this yet, but you can do things that can take messages and optionally respond to them or not, depending on whether they obey certain conditions, or other things obey certain conditions. And that's a good thing to be able to do, which is, again, central to what computers know how to do, or how people think about programming computers, and which is much more appropriate to this regime of messages than it is appropriate to this regime of signals. Right? So why bother with signals at all? Well, so that you can do computer music, because computer music, eventually you have to make sound, and that's signals. So this world is less flexible, but it is the correct place to be if you want to do something like have an oscillator. There is no OSC that doesn't have a tilde. It doesn't make any sense really to do that in message land, because it depends on having a sample rate in order to know what to do. All right, questions about this? So these are the two. So this is what loop looks like in some way of thinking, both in message land and in signal land. And now that I've told you that, I want to go back sideways and start looking at tables again as sources of waveforms, because it's time to start doing sampling. Sampling is actually no different from waveform oscillators, except psychologically. But at times there are things that you want to do with samples that are more easily done using messages than using just a phaser that rips through things. Including, I should say, the next assignment, which I don't have the heart to show you because I don't think many of you finished homework 3. I'll show you homework 3 with the extra credit done correctly this time, at least in output, so that you can see what you should be listening for. But homework 4, at least to do the extra credit thing, I think you're going to really want to do it with messages and not with a steady going signal, because there might be decision making to do. All right, so this is what this is, and I'm going to save this and then immediately start doing sampling. New. Okay, so to do sampling, you will need some new objects. In particular, well, yeah, you're going to need these two. The sound filer, I don't want to show you just yet how to do live recording into PD, because that's going to be another thing. It's going to be easier and anyway more urgent to learn how to get sound files in and out of arrays. I've shown you now, I think, 4 ways of getting stuff into arrays, including reading from a text file. But of course, when you're doing computer music, you're going to have these recorded sound files that will be in WAV format or AIFF format or whatever it might be, and you're going to want to get it into your arrays so that you can have them as waveforms that you can play them as samples, say. So that's a fundamental thing that you might wish to be able to do, and so I want to show you how you would set about doing it. So let's save this. Actually, both before and after I saved it, I want you to enjoy the fact that it does live in a directory, which here is going to be my Linux style home MSP and then whatever. And this directory is going to be where PD looks for file names. This you first saw when I used the read message to arrays in order to read a collection of ASCII numbers or text numbers into an array. And the same consideration will hold here. The directory that I am in, I've already moved a sound file into the directory that we're in right now. Which maybe you'll see if I say open, except maybe it only shows PD. Yeah, I can't ask it to do all files. You won't see that. All right, I could go figure out using the Finder how to show you the directory contents. But anyway, let's just look at it. So, all right, so we'll make an array, as we always do, or as we often have. And I don't know why I bother with that. I'm going to say, let's have 100,000 points. That's a little over 2 seconds of sound. And it's going to be table January 25th B. Blah, 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 blah. Okay. And of course, there's this bug where it forgets that I told it that I wanted points. Don't know why. Alright. And now, read sound file into it is done by a separate object. You don't pass a message directly to the array. Instead, you make an object which is called soundfiler. And you send it a message which is read again, and it's going to have the name of the file. Ooh, there's a dot there. That's the name of a sound file that I've got. And then it needs the name of the one or more arrays that I'm going to fill with the contents of the file. And 1.2, oh, I forgot the T. Don't need the T. Ta-da. Alright, so what I did was I just loaded the voice.wave thing in here. If you want voice.wave, it's in PD. For you Macintosh users, you option click on PD and say show package contents, and go looking in the documentation. There's a thing called voice.wave, which is this file, which is included in the PD distribution just so that some of the example patches in the PD documentation will work, and also so that you can have a sample sound file to do stuff with as you start to make patches before you have worked out your microphone situation. The microphone situation is kind of miserable with people who own, or for people who own laptops, for reasons that you might already have discovered. For instance, you can't type and record at the same time because typing makes a very loud noise that goes to the microphone, and things like that are bad. So, so give yourself, if you want to do stuff with microphones, give yourself some time to figure out what kind of microphone you need and buy it and how you're going to have to connect it to your computer. It's not going to just happen tomorrow. All right, so Soundfiler also takes messages to write the thing back to a file, and it will deal with files of, all right, it likes WAV files, which is the closest thing there is to a standard PCM file format. It will only deal with PCM files. It doesn't know how to do MP3s and stuff like that, which are data reduced using proprietary algorithms that well, you can find out what they are, but who wants to write the code to deal with that? And it will also deal with .AIFF files, although AIFF files, I'm frequently confronted with AIFF files of one sort or another that where they've changed the header a little bit and PD can't deal with it anymore. So PD is not as successful in reading AIFF, which are the Macintosh files, as it is reading the PC files. So if you can't read your file in, just convert it to a .wave, and then it'll be perfectly happy to read it for you. The Soundfiler has no idea, well, sorry, the array has no idea what sample rate the thing is that it holds. And with that in mind, Soundfiler actually ignores the sample rate of the file. And a frequent beginner's error is to go off on the web and find some nice file of a dog barking or something, download it, verify that it's PCM, but not notice that it's 8 kilohertz. A lot of files on the web are 8 kilohertz. And then if you try to play it at 44K1, it will sound some octaves higher than where you wanted it. Yeah? Oh, properties of the graph. Yeah, I should just sort of systematically do that, shouldn't I? So, what I've got is Y's ranging from -1 to 1 and 100,000 points. So if you're operating at 44K, this is a little over 2 seconds. And the reason I gave it that number was because I happened to know that the sound file I was going to read in was 1.5 seconds or so. So that was kind of a reasonable number of points to give it. Oh, yeah. If you want to, let's see, let's get rid of this. Oh, yeah. Save contents. If I save the contents now, there will be 100,000 numbers in the patch. And the patch itself, I don't know if you've noticed, but they tend to be less than a kilobyte at this stage of the game. So this would like multiply the size of the patch by more than 10. So when I'm using sound files, I don't save the contents. All that means is that when oh yeah, let's save this. This is going to be 3.sampling1, because we'll have many sampling patches. Sampling is not just one thing it's going to turn out. Okay. So now when I reopen this patch from nothing, there it is, but it doesn't have the sample anymore until I do this. And now, the thing that I will urge you to do when you're doing this kind of thing is say load bang. So that when you open the patch the next time, it'll open the patch and then the load bang will say bang right when it loads, and then it will read the table in. So this is a complete thing. Really should have two files. It should have voice.wave and it should have the patch. The patch shouldn't have voice.wave in it, which would be ugly and messy. Instead, the patch should be set up to read the thing in on loadup. All right. So now that we have that, I'll just actually check that it happens. There it is. So, and I guess your way of verifying that this thing really loaded instead of not is disconnect this and see that it's 0 again. Or else, if you believe it, look at the dialog window for the array. All right. So this is getting sound files into arrays, and of course we're doing that so that we can act like a sampler. All right. Sampling is reading out of the array, which to start with I'll do the bad way and then I'll do it the good way. So I gave you this harangue earlier about non-interpolating table lookup being a bad way of reading samples or tables, and it was hard to actually hear the badness because I was using sinusoids. It'll be easy to hear the badness when I start using real sounds, I think. So here now is listening to this sound file. So what we're going to have to do is say tab read tilde voice.wave. Oh no, wait, I'm sorry, I gave the not the file name, the name of the table. Okay, and now I'm going to give it a signal which ramps from 0 to 100,000 in some appropriate amount of time. So an easy way to do that, let's do it wrong first. I'll just put a number box here, and then we'll listen to it that way. Now, just looking at it, this thing has an amplitude of about 0.3, which might be loud in this room, so I'm going to multiply this by another 0.3 to drop it to 0.1-ish. I could do, it would be better if I did something controllable there, but this will do for now. And now we listen to the nice sample. Now, what this means is take the 134th point of the table. That's right about here. Right? If I want to hear what this is like after a second had passed, I have to put 44,100 in there. There's the sound of sample number 44,100. And yeah, my audio system doesn't like this very much. Okay. All right. Yeah.
Is there any particular place, like I renamed just a random wave file, voice.wave, and put it in my P folder?
Yeah.
Would there be any reason that it says could not find no such file or directory?
Okay. Beginner's error would be the patch itself doesn't know what directory it lives in. So save the patch into the same directory. Oh, so the patch should tell you what directory it is here. And if it says something like, if it doesn't say anything there, or if it says / or something like that, then it's looking in the wrong place. And the way to fix that is to save it so that it will know what directory it belongs in. That was a very useful question to ask, because that happens to about 2/3 of people the first time they try to read a sample. If indeed that was the thing that would just happen to you. Maybe, right. Find out. Otherwise, you belong to the other 1/3 that got past that one and hit the next thing, whatever it turned out to be. Okay, so this is bad. You can't just do this and expect to hear a nice continuous sound, right? Why? Because, well, you probably know this, but mice update from 50 to 100 times a second, depending on your OS and how hard you're mousing. And of course, that's not going to sound like a continuous signal. It's going to just sound like a bunch of glitches. Okay, you could like that, of course. So what we have to do is do something continuous like this. Maybe we'll say line tilde and feed it a message to, let's see, I'll feed it, I'll do this a variety of ways. First off, I'll do the stupid thing, which is, oops, sorry, go away. Feed it a message which says jump to 0 and then slide to 100,000. Now, over how much time? What is that in seconds if it's 100,000 samples? We'll find out. This is acoustics, by the way. You should have learned this in acoustics class. So we'll say my favorite calculator program. So what's 100,000 samples, which means we divide it by 44,100, and it is 2.2676 seconds long. If I were not doing this pedagogically, if I were just doing this, I would just make my patch compute this thing automatically, but that would be more boxes messing around on the screen, and so I wanted to show you this way first. So the appropriate length of time to read from the beginning to the end of the table would be 2,268 milliseconds, roughly. Not exactly accurate, but good enough for today. 2268. So now I go back here and say, you have 2,268 milliseconds to do this.
Continue with soft and relaxing.
And then we get sample. All right? That's KC95, in case you don't recognize it. Oh, it's KC95 with some announcer who was announcing 10 or 15 years ago, so you probably don't recognize it. All right? So, oh yeah. Now we'll just, here's the thing that I've seen people get confused by. If you just say, do that, you don't get anything, because the line tilde is currently putting 100,000 out. It's 100,000 volts if you were an analog synthesizer. You'd be arcing at this point, right? So to slide from where it is to 100,000 is basically to continue doing nothing, or to continue putting out your 100,000 volts with no variation. So the correct way to hear it again is to go back to 0 and then from there to ramp to 100,000.
Continue with soft and relaxing.
And then you get the nice ramp. Sorry, it's a little loud. I'm going to turn it down a little bit.
Continue with soft and relaxing.
All right. Now, either to clarify this or to further muddy it, depending on whether you personally find this clarifying or muddying, this will be different for different people. Here's how you play it backwards. Let's go to 100,000. That makes the line jump immediately to 100,000, and then let's ramp to 0 in 22,068 milliseconds.
All
right, and then we have it the other. Oh, and by the way, notice that there was a good 3/4 of a second of silence there. It's reading the zeros at the end of the table.
All
right.
Continue with soft.
All right. That's useful already. Okay, now is it clear to everyone why this is doing what it's doing? So in one way of thinking, the x-axis here is labeled from 0 to 100,000. The y-axis is the voltages which comprise the sound itself, and we're asking it to go from left to right, and we're giving it an amount of time. So now if I wanted to play it transposed up by a factor of 2, that's to say an octave, what would I change and how? Someone said something, but I didn't hear it. Yeah? The time. Yeah. So if you want to go twice as fast, you do the same thing, but you do it in half the time. 1, 1, 3. Look, all the digits are even. I don't know why. And now instead of this,
Continue with soft and relaxing.
we get this. All right? Okay, and now we've basically got the sampler functionality. And I was telling you this was going to sound horrible, but I have to work harder than this to make it sound horrible, because actually dropping every other points of a sample, that would cause foldover, but that wouldn't cause the bad foldover that would make you really think that I was doing something wrong. A good way to make it sound wrong might be to go at 1% wrong speed, like this. 2240. Here's about 1% too fast. So here's the good sound.
Continue with soft and relaxing.
And here's wrong.
Continue with soft and relaxing.
Any problem with it?
Continue with soft and relaxing. Continue with soft and relaxing.
All right, I can't make it fail. Let's make it, okay, I'll make it fail. What we're going to do is we're going to put an oscillator in here. The oscillator is going to have a nice, decently high frequency, but not high enough to be painful to most people, I hope. And I'm going to not do it at full blast. I'll do it only about 0.3-ish to have similar amplitude to the sound file. And then we're going to use the fabulous tab right tilde object. And then we need a button to tell it to go. Yeah, there's a nice sinusoid. All right, now here's the good sinusoid. Oh my. That was horrible. Oh, so even this is wrong, because this isn't the exact number. So once in about 2,000, no, once in about 6,000 or 7,000 samples, this is not working right, and you're even hearing that. And now if I push it a little further off, that's the rate at which it's dropping samples in order to get it done in a few milliseconds fewer. All right? And that is not, you know, they'd pay you for that in a club, but they wouldn't pay you for that in a classical music concert. Right? Okay, so this could be a good reason to reach for this object here. Oh, isn't that a horrible? That's me putting out, I'm still putting out DC here, except that when I move this, the computer is having to redraw the table, which means it's putting out zeros, because the operating system's getting hungry for samples, and as a result, I'm hearing a huge discontinuity in the sound. So that's bad. That would be a good reason to put this thing in a sub window if I were going to do this during a show. Right. Okay, now, okay, so compare that to this. Let's see, I'm just going to get the, oh, you know what, I'm going to do this right in this one, which has all the good examples, and then I'll make the bad one so you can compare it. The 4, as you might or might not guess, means use 4-point interpolation, which means put a cubic polynomial through the 4 points immediately surrounding the point that you're asking for to give you theoretically a more accurate estimate of where the function would be at that point if it were a nice 4-time differentiable function. Anybody's guess whether it really should be such a thing. Okay, and now I'm going to still want that in this. Let's see. So here now is the bad result. And, oh my, and here's the good one. Or here's the first error I had. Whoops, no wait, this one. The one that made a few dozen errors a second. And that's as to compare with this. All right, so interpolation is your friend. 4-point interpolation, yeah. When did I put the sine wave in? I used this network right here. Yeah. Oh, right. So now if I want to go get the sound file back, I would do this. And now, oh, by the way, this is always playing right now. So you hear clicks when I change the table. You should probably have some way of muting the amplitude if you were doing this for real. And don't worry, you can make things arbitrarily complicated later to make it nice and clean. And then here's the sinusoid back. Ugh. All right. So now, the moral to this is use tab read 4 instead of tab read 4 tilde instead of tab read tilde for reading audio data out of arrays if you want the result to sound clean. And then the other thing to be hyper aware of is it might be as dirty as goats and you don't even know it because the sound itself is complicated. So test your patch out with sinusoids first to verify that your patch actually does good things. Otherwise, you might convince yourself that it sounds great, but it doesn't and you don't know it, which is not a good state to be in. So it's better to apply stringent tests with very simple signals so that you hear things clearly. And in fact, now that I'm saying that, now that we've got the voice in here, I'm not even sure it's going to be audible in this room, the difference between correctness and incorrectness. So here's incorrect.
Continue with soft and relaxing.
That's dropping the samples at the same rate like that, and you don't even hear it.
Continue with soft and relaxing.
Maybe you can convince yourself that you hear it, but then it even might be true that you're just imagining it.
Continue with soft and relaxing.
I don't think I can hear it at all. And that's the wrong one. This is the right one.
Continue with soft and relaxing.
And by the way, let's subtract them, and we will hear only the error signal. So I'm going to take this one and give it an amplitude of minus 0.1 and this an amplitude of plus 0.1 and start them simultaneously. And there's an error signal for you. That was an aside. If you didn't understand that, don't worry about it. Questions about this? Yeah.
I missed the part where you came up with the third value of the message boxes.
Oh, yeah. Okay, so, right. So the message box has 2 messages in it, and it's describing a line segment. Well, okay. So it's describing a start point, an end point, and a time to do it in. And the third value is the value of time over which to ramp. Yeah.
So repeat these to resample accurately and processing. So like right now.
Oh, yeah. Right. So yeah, if I put a few hundred objects on one side and then 3 objects on the other, would the signal get faster through the 3 objects than through the few hundred? The answer is no. However, there are ways that I haven't shown you yet that you can in fact accumulate delays without knowing it. And so there's one particular thing to watch out for there, which is when you make non-local signal connections. Sometimes you don't know that they're instantaneous. Yeah?
Can you explain what interpolation is?
Yeah, I should have started out by doing that. Okay. Back in the 70s, when I was studying algebra, they taught you this because you had to learn how to read tables of logarithms in order to know how to multiply numbers because people didn't have calculators. But people might be forgiven for not knowing this widely now. So interpolation is the following thing. You've got a table of logarithms, and it's printed in the last 5 pages of your Algebra 1 text or something like maybe Algebra 2. And you really want a logarithm to 6 decimal places of accuracy, say. So how do you do it? You're not going to get it just by looking the values up in the table, because just looking at them one next to the other, they're changing by 0.1%, say, from each one to the next, because there are only perhaps 10,000 of the numbers printed for you. And what you want is one that's between those 2 numbers. So what do you do? Well, you know how far it is between the two numbers, and so you just draw a straight line segment between them, and you know how far along the segment you want to be, and then you can use some elementary algebra or geometry to figure out then where that line segment would be at the exact point that you asked for. So in the memory, and this is in general true about any digital signal processing, you only know the value of the function of the signal at specific discrete points. And sometimes you want to know what it would be between two of the points. And so how you do it is you say, well, we'll put a line segment or something like that between the 2 points of the table. And if we're 0.3 of the way between this point and the next one, we will take this value plus 0.3 times the difference from this value to that value. Okay? And then it gets better because that works okay, but that doesn't work well enough so that you can guarantee that the error is inaudible for, say, a sinusoid going at a kilohertz in a very good studio. So you could say, I know it's between these 2 points, but I actually want to put a what do you call it? A parabola, a second degree polynomial between 3 points to estimate not just the slope between the 2 points, but also the second derivative. And that might or might not give me an even more accurate value. And that is called the order of the interpolation, how many points, or how many, the degree of the polynomial you're using. And tab read 4 is 4-point interpolation, which is, I think correctly, called third order, which is to say it puts a cubic polynomial through the 4 surrounding points, surrounding whatever non-existent point you've got. And that is what tab read 4 tilde is doing for you. And if you look in the book, I don't want to go fishing through it right now to find it, you will actually find quantitative estimates of how high a frequency you can actually store in the table and get decent values using tab read 4. It's actually not really good enough, even though I can't prove it to you in this room. As soon as the period of a sinusoid is at least 32 points here, it's pretty much a guarantee that tab read 4 tilde will give you inaudibly small errors. But the Nyquist frequency is, which is the highest frequency you could possibly represent, has a period of 2 points. And at the Nyquist, even throwing a cubic thing through the 4 nearest points has trouble giving you the values correctly. They'll be incorrect. The good news is that people don't have signals that are loud at the Nyquist frequency very often. And so that's not very often a serious problem. Let's see. So the period's 32, and if we're at 44 kilohertz, that means components up to about 1500 hertz will have truly inaudibly small error, and components above that will actually fold over gradually more and more until you get up to 20 kilohertz. The fold over is getting quite significant. And if that's a problem, which it usually isn't, but could be, then take the signal and resample it so that its true sample rate isn't 44K1, but is 196K or a million. I mean, you can sample as high as you want. And so you can actually get arbitrarily low errors using oversampling here. But it turns out that at that point, oversampling is a better strategy than adding more points to the interpolator, I think, in most cases. Me, in practice, I just use tab read 4 tilde and don't worry about it, which is, of course, what I just told you not to do. But you should actually check it and, all that kind of stuff. Sorry? No, there isn't. Life's too short for that one. If you look at the formula for cubic polynomial interpolation, it's already about a line long in C. And the one for 8 points is, a paragraph long. It would be a lot of computation, and it would be a serious head scratcher. And by the way, at that point, you get into serious questions about whether doing a polynomial interpolation is better than doing something else. And so then you would have to have all sorts of different flavors of interpolators, some of which were better suited to some frequency ranges than others, and then you would just be in a morass of horrible detail. So my advice is just don't go there. And I don't even know if anyone has made higher order interpolators for PD. If you want one, go looking, and if you find one, tell me, because I'm curious too. All right. So, yeah, let's see. I think that's all I better tell you right now about sampling. I'm going to tell you a bunch more later. Oh, I should say one small thing about this, which is just to tie this to what we've seen earlier. This is the message-based way of sampling, which lets you do this kind of stuff.
Continuous, soft and relaxing.
I just whacked it a few times. Every time I whacked it, it was already running through the sample, but I just made it stop, go back to the beginning, and start over again. So that would be appropriate to, for instance, you want to play something every time a network packet comes in, or a key goes down on the client or keyboard, or something like that. Right? You can also drive these things in the other way, which is to say, make the whole thing be a signal network, like this. Now I need room. And I really want this to be part of the same window for pedagogical reasons. So I'll just make the window absurdly big. Okay, so another thing that you can do is take the tab read 4 tilde again. All right, I'll do this. And let's just read it with a phaser, just like I showed you how to do with tables. Of course, you don't really do this. Let's see, let's give it a frequency, which will be a number. This, of course, will give us not a whole lot of anything, because it'll be reading the first point of the table over and over again, which gets us nowhere until we start multiplying it by something. And now, just to remind you, if I give you a phaser that goes from 0 to 1, but I want a phaser that goes from A to B, the thing that I do is multiply by the size of the segment I want, B minus A, and then add A. Right? So we need now to multiply. That's what I'm going to do, is rearrange this. So we'll multiply it by something, and I'll just have a message box to decide what. And then we will add something. Sorry, number box. And now, for instance, if I want to say, okay, we'll do 10,000 points worth, please. 5,000 points worth. Okay, that's the C out of continuous. And now if I want to change where I am, let's go faster. Now if I want to change where I start, I'd change this number. Right? Or in fact, you can even sort of do this. Okay, now let's make this shut up. Actually, I should say these numbers are in samples, right? Because tab read 4 needs its input in samples, and number boxes, operate as, they're good for values around 0 to 1,000 because it's a pixel a number. So it's a good idea when you're doing this to rearrange the number boxes by multiplying by some suitable number, which this morning anyway seemed like 100 was a good number. So let's do that. And now we have a much better, much more mouseable little sampler. Okay, so what do I have to manage? Oh, it doesn't do it. Oh, wait. Oh, man. Sorry, that was wrong. I want it to go on this side. And by the way, I polluted the value of 100 in that box, so I'm going to retype the number to make sure it still works. Now it's 50-ish. Okay, enough of that. So, all right, there might be some cleanup work to do if you want to play this in a classical music setting, but So what we're doing now is this is the same thing as this,
Continue with soft and relaxing.
except that here it's entirely a signal network. It's a phaser tilde, which is simply scrubbing over and over and over again. It's not going to wait for me to get a message box at this point. It's automated. It's less flexible, but at the same time, it's easier to put together, and it's easy to do things like change the frequency in the middle of a segment. Like here, I wouldn't be able to do something like, say, have it go up in frequency as it was going through. It could, but it would be a lot of work. Here it would be easy. I'll just say, let's do this in a half, once per 2 seconds, and we'll start at 0, and it'll range over 2 seconds. Oh, but I have it in hundreds, so that's 882.
Continue with soft and relaxing. Continue with soft and relaxing.
And now I
Continue with soft and relaxing. Continue with relaxing. Continue with soft and relaxing. Continue with soft.
and even backwards. Now this would be harder to do with the message boxes.
Soft and relaxing.
Okay, let's shut up. All right. So that's just a different thing that's just a different way that you might want to do it. And sometimes you want the one and sometimes you want the other. And frequently and unfortunately you might want aspects of one and aspects of the other, and you will have to make a difficult decision about which path to take. And some aspects of what you're doing will be easy, and others will be things that you wish you were in the other regime to be able to do. And that is, as far as I can tell, just sort of a fact of life about computer music. All right, so it's clear what the distinction is that I'm making. And this one, you could change what it was doing in midstream easily, but you couldn't jump it back to the beginning. Well, you could actually. You could just bash the phase of the phaser, but there would be things that would be harder to do this way. And there are things that would be harder to do this way. All right. Let me then go back. What I want to do is ask for, well, just make sure that you hear the assignment 3, which is due Thursday, and understand what's going on there. And then I'll show you assignment 4, not to demoralize you, but in order to show you why I'm showing you all this. Actually, why don't I do it in the opposite order? Let me show you assignment 4 real quickly, because I'll show it to you again in more detail later, and then go back to assignment 3. So I'm going to save this and close it. And open homework 4. Homework 4 is just to, oh, it doesn't work. Oh, because I had a table named pitches inside here. All right, that means I have to close somebody. This one, no, this one. I just don't have to close. Let's close everything. Oh, I have 2 copies of this open. Wonderful work. Okay. And does it work now? All right. So we're making the poor radio guy sing a little boogie. All right, this is really stupid, but I tried to make it sound good using a very simple set of objects, and couldn't. I could either make it hard to do, or else I could make it sound bad, and I decided to make it sound bad so it wouldn't be terribly hard to do. But if you want it to be hard and to sound better, so this is, oh, what's bad about that? Well, there are a lot of things bad about that. Okay, here's an alternative thing that sounds a lot better, but is much harder to do, which is to arrange that it actually make 4 copies of the sound every time, for every pitch of the boogie, which is going to require synchronization. Let's see, and then you get this. Okay. So that's a proper sampler in some ways, and that will be harder to pull off than just making the thing loop at different speeds, which is the basic homework. Okay, so think about how you want to get there, and now I'll go back and play you the other homework assignment, which is really the one due next Tuesday. Oh yeah.
Is that going to be on
No, because this implements it. So this is my secret how I did this. But what I'm going to do is put the description of how to do it, like the other homeworks. I put up a description of what I want the thing to do, and sound file showing you how it sounds when you've done it right, and then I make you work out the details to make it work. Yeah. Otherwise, you just copy and paste the patch and turn it in. Okay, so here's the homework for this time, which also comes in easy and hard forms, but they're actually part of the same patch this time around. Let's see, I think it's this one. Yeah. So I played you this already, but I didn't have the extra credit working quite correctly. Actually, is this working? Yeah. This is now it's just 8 notes. By the way, since bringing this out, mute doesn't work today. Since bringing this out, I told you how to do M to F to convert MIDI numbers to frequencies, but you can probably hear that these are not MIDI frequencies. I just made multiples of 110. These are harmonics instead. But you don't have to figure out the melody. You just get the effect and make your own wonderful little melody. I will say that it works better, as I discovered by trial and error. It works better if you keep the thing within an octave than if you just have the thing flying all over the place, because, well, I don't know. Anyway, somehow the phasing effect is more effective if the intervals when they're out of phase aren't too crazily big, which means the melody itself has to be within a decently small range. This is within a major sixth, I think. Yep, that's streaming. That's music 175. Right. Oh, and it's also history of electronic music because it's phase music. Yeah. And why don't my mute buttons work today? Okay. Here then is the. No. There's the stop button. I should have labeled them. Here's the extra credit. This is really cruelly difficult. Don't even try this unless you want to be frustrated. So here the idea is take each one of the individual melodies, and every third note of it should be a substantially different timbre. So it's the same melodies. Well, it's at this big, right? But of course what you hear is, right, which is every third one. So you actually hear a sequence of 8 things going at this speed instead of the real speed the thing's running at, right? Okay. The way I did this without using stuff that I haven't shown you how to do. Well, my mute buttons are all not working today. I don't know why. Okay. The way I did this was I had 2 different generators, one of which was just a sinusoid, and the other of which had I think 3rd and 4th harmonics, and none of the 0th harmonic, which you can do with sine, cosine tilde and phasor. And then if you want to shut it up, rather than try to multiply it by a thing that ramps down to 0, which would be hard because it's driven by a phasor, I just bashed the frequency to 0 to make it be quiet. So each one of them has a frequency that is 0 when I want it to shut up and non-zero when I want it to hear that one. And that's why it sounds so ragged. Those popping sounds, that's the sound of a sinusoid or another simple spectrum suddenly having its frequency bashed to 0. You can't really do that. Okay? And then make 2 of those and make them do the same phasing thing. Let's see, let's shut it up, and I think these things will start in phase if I just start it up. Okay, do it like that. Oh, sorry. And now you can either hear this at this speed, or else you can hear it at this speed, and you have phasing effects going on at both speeds. And so it takes 30 seconds for it to repeat or come back to the initial phase. doesn't sound like it ever's gonna. Oh, there it is. I think. Not sure. All right. And if you can do that, then you might have something that you enjoy listening to. Oh, also, if you play this over your computer speakers, you won't hear those glitches quite so badly because they are low frequency. And your little half-inch computer speaker won't play that. So that's a better description of what the assignment is than I gave you last Thursday. This is all up on the website, but frequently I write something on the website and think it's totally clear, and then when people read it, they don't find it anywhere near as clear as I thought it was when I wrote it. So when that happens, just ask, either by email or by asking in class. Questions about this? Yeah.
Do two tables that have the same notes, or is it just one you're reading it?
The way I did it, I wanted to do it in a way that allowed me to change the two numbers, and so I had to work very hard with modular arithmetic. I actually did the whole thing with 1 8-note table, but then I did trickery to make it drop 2/3 or 1/3 of the values out of the table to 0. And you actually know the objects to do that, but it might take several hours to figure it out. So the thing you get out of that is I can now do 7 against. Whoa, that's not 7. Hey. And so on like that. Oh yeah, and now it makes sense to make this number 2. So if you're crazy like me, you would do it that way, and it would be much harder than just what you're suggesting, which is just have 2 tables and make it easy. But you can have a lot more fun with this one.
Is that the same for the first, not the just the original assignment?
The original assignment doesn't have anything corresponding to that too. So in fact, I did use. Oh, the original. Yeah, I did it in the same patch, so it is working the same way. So I think I can make this now be 5, and it should just work. No, it doesn't. Why not? Oh, it went to 0. Why does that happen? Yeah, but okay, yeah. And I figured out where in the sequence to start so that it was interesting with any number from 3 to 8. So I went much too far in messing around with this. It turns out to be very interesting to play with. But yeah, stop it. What do you say? Patch responsibly.